Before we talk about the sun and stars, we need to talk about radiation and spectroscopy. When we say radiation, we're talking about emission of energy in all directions, that is, radially. Here we're just going to focus on two types of radiation. First, electromagnetic radiation, that is, radiation of photons or particles of light. These are also sometimes called gamma particles, but they can be at any part of the electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, or gamma rays. Although photons don't have mass, they still carry momentum and energy. And because they are light, they travel at the speed of light. Second, when we talk about particle radiation, we're referring to particles with mass. Alpha particles, which are basically helium nuclei, consist of two protons and two neutrons. There are also beta particles, which are either electrons or positrons. A positron is the antimatter counterpart of an electron and it has a positive charge but the same mass as an electron. And particle radiation could also include neutrons or protons. We can relate radiation from an object to that object's temperature. As an object's temperature increases, the object radiates light more strongly and at shorter wavelengths. When we talk about objects in physics and the radiation from them, we often like to idealize those objects, and we call this idealized object a black body. A black body absorbs all electromagnetic radiation, no matter what wavelength or incidence angle. A black body turns out to be a very good approximation for stars and planets. This plot shows black body radiation for objects of different temperatures. The vertical axis says spectral energy density, but you can just think of that as brightness. The horizontal axis here is wavelength. You can see that the object that is 3,500 Kelvin is the least bright, and its peak wavelength is around 800 nanometers. As we move to the other objects, 4,000 Kelvin, 4,500 Kelvin, 5,000 Kelvin, and finally 5,500 Kelvin, we can see that they're getting brighter, but also the peak of that spectrum is moving to the left. That means it is at shorter wavelengths. We can relate the peak wavelength to the temperature through Wien's law. The equation is lambda peak, the peak wavelength, equals B over T. T is temperature, B is a constant, approximately 2,898 micrometers Kelvin. When photons are absorbed or emitted from atoms, electrons change the orbitals they're on. You could think of electrons in an atom as being very picky, and their tastes depend on what type of nucleus they are surrounding. Because electron orbitals are quantized, an electron requires a very specific amount of energy to jump up to a more excited state. It can only absorb energy that can bring it up exactly to another orbital. Electrons also release energy at a specific amount to go down to a lower orbital. So let's say an electron releases some energy to go down to a lower orbital. The amount of energy it releases in the form of a photon corresponds to a photon of a specific wavelength. Because that specific amount of energy it released is related to the wavelength of the photon through this equation of E for energy equals h, the Planck constant, times c, the speed of light, divided by lambda, the wavelength. For example, in a hydrogen atom, an electron that transitions from the third orbital to the second orbital emits light at 656 nanometers, which is in the red part of the spectrum. Spectroscopy, then, is the analysis of an object through its spectrum of light. We collect light from stars, and we can look at that light. Light from a star will be predominantly a continuous spectrum, but there will be some absorption lines that correspond to elements that the light has passed through on its way to us from the star. But if we're observing from the ground, then absorption lines will also reflect what's in Earth's atmosphere. The emission lines and absorption lines on this slide correspond to hydrogen. And there's more hydrogen in the universe than all the other elements combined. In general, a star is a luminous spheroid of plasma held together by its own gravity. The total mass of a star is the main factor determining its evolution and fate. The star has to be massive enough to have a hot enough temperature in its core for thermonuclear fusion. The fusion in its core is what causes a star to shine. A body has to be at least 13 Jupiter masses to be capable of deuterium fusion in its core, and that would qualify it as a brown dwarf. The more massive a star, the hotter its core temperature will be. Due to the electromagnetic force, protons repel each other, but at higher temperatures, they move faster. So at a hot enough temperature, they can overcome their repulsion and fuse together. There are two types of fusion of hydrogen into helium that occur in the cores of stars. The proton-proton chain, also known as the PP chain, starts at around temperatures of 4 million Kelvin. This is the main pathway for nuclear fusion in our sun's core. The process begins with two protons getting close enough to each other to fuse, and one of them turns into a neutron, and they emit a positron and a neutrino. Then we have deuterium, one proton and one neutron together. And if another proton comes by, it can fuse with them to form a helium nucleus, but that process releases a gamma particle, a photon. While that's happening over here, let's say it happens again at another place close by, then we have two helium-3 nuclei, called helium-3 because they have only 3 nucleons. Then those two helium-3 nuclei fuse together. Two of those protons are released, and we're left over with a helium nucleus, or an alpha particle. And we have left over 2 protons that can begin this cycle again. For stars that are 1.3 solar masses and above, the CNO cycle is more efficient. Let's say there's a carbon nucleus lying around and a proton is nearby. They can fuse, emitting a photon and forming a nitrogen nucleus. After a certain amount of time, one of the protons in that nitrogen nucleus can decay into a neutron, releasing a positron and a neutrino. Then it's carbon again, but now it's carbon-13 because there's an extra neutron. Now, if at this stage another proton comes by, then it releases another photon and becomes nitrogen again, but this time nitrogen-14. This is more stable than nitrogen-13. And it can be stable long enough until another proton comes by, and a photon is emitted, and then we have an oxygen-15 nucleus. Oxygen-15 isn't stable, so after some time, a proton decays into a neutron, again emitting a neutrino and a positron. and we're left with a nitrogen-15 nucleus. When a proton then comes by that nitrogen-15 nucleus, an alpha particle breaks free. That's a helium nucleus, and we're left over with carbon-12 beginning this cycle again. So in both cycles, we need 4 different protons to come in at different stages, and we get 1 helium nucleus as a result. But these take different pathways. Both of these pathways are happening in our sun, but the CNO cycle accounts for only about 1% of the helium produced, because the sun's core isn't hot enough for the CNO cycle to be that efficient. Stars that are fusing hydrogen into helium in their cores are called main sequence stars. Most of a star's lifetime occurs on the main sequence, but after a star has aged and exhausted the hydrogen in its core, it can move on to other stages. If a star is massive enough, it can fuse other elements beyond hydrogen and helium. That would require hotter temperatures, and it would also take less time for those stages. For example, a 20 solar mass star would first go through its main sequence, fusing hydrogen into helium, requiring a temperature of 37 million Kelvin and taking about 8.1 million years. Then, moving into the red giant branch, it would fuse helium into carbon. That requires 3 helium nuclei. It's called the triple alpha process. And that requires temperatures around 188 million Kelvin. It would take about 1.2 million years. But then the star is approaching the end of its life. The carbon fusion cycle takes less than 1,000 years. Then there's a brief neon fusion cycle and an oxygen fusion cycle and a sulfur and silicon fusion cycle. The end result of silicon fusion is iron, but iron won't fuse with other protons and neutrons to get larger elements unless a lot of energy is nearby, because energy is required for that to happen. We're talking quantities of energy that are only available in a supernova, which we'll talk about next time. The internal structure of a star consists of convective zones and radiative zones. Convection is energy transfer by bulk motion, and in these diagrams it's depicted with loops with arrows. Radiation is energy transport by photons or massive particles, and radiative zones are depicted in these diagrams with the zigzag arrows pointing outward. For example, a red dwarf star with a mass less than 0.4 or 0.5 times the mass of the sun will be all convective, which prevents helium from accumulating in its core. In the middle, a yellow dwarf star, like our sun, has a radiative core and a convective shell. And then on the right, a blue-white main sequence star with a mass greater than 1.5 times the mass of our sun has a convective core and a radiative shell. What we might think of as the surface of a star is called the photosphere. And then above the photosphere, the atmosphere of a star has 4 main regions. The chromosphere, transition region, and corona are all hotter than the photosphere. Chromos in Greek is color, and the chromosphere is visible as a colored flash at the beginning and end of total solar eclipses. The temperature in the chromosphere increases gradually with altitude, and it gets to about 20,000 Kelvin. Then the temperature in the transition region increases rapidly with altitude, from about 20,000 Kelvin to 1 million Kelvin due to helium ionization. Then the corona is even hotter, and we still don't know exactly why, but it probably has to do with magnetic reconnection. The corona of our sun is visible only during total solar eclipses. Outside of the corona is the heliosphere. The heliosphere is filled with the solar wind plasma and extends from about 0.1 AU to about 50 AU, the heliopause. Beyond the heliopause is interstellar space. It's possible to see sunspots without a telescope, but do not look at the sun without proper solar filters. Sunspots are protrusions of the magnetic field. On the sun, sunspots appear and disappear in an 11-year cycle. Because the sun spins with differential rotation, its layers spinning at different rates, the magnetic field lines get twisted, and after about 11 years, the sunspots disappear and the magnetic field resets itself, but this time upside down from where it was before. When we want to talk about how bright a star is, there are two things we could mean. We could mean, how bright does it appear from Earth? Or we could mean, how luminous is it in an absolute sense? Brightness is an apparent measure that decreases with distance according to an inverse square law. We could use the equation brightness equals luminosity divided by 4 pi times the distance to that star squared. Luminosity is the absolute measure of a star's radiated electromagnetic power. The luminosity doesn't depend on how far away that star is from Earth, but rather it's a physical characteristic of the star itself. Through spectroscopy, we can classify the stars into different types. It turns out that these types correspond to the star's temperature. And by the star's temperature, we mean the temperature of its photosphere, not of its core. The main spectral types of stars, in order of temperature from highest to lowest, are O, B, A, F, G, K, and M. Recently, a few other spectral types have been added to the right of M, L, T, and Y, but we don't have to get into those. We can collect the light from a star, look at its spectrum, determine the peak wavelength to know its temperature, and also see where the absorption lines are to determine its metallicity. Combining our knowledge of a star's luminosity and temperature, we can place it on a Hertzsprung-Russell diagram. This can also be called an HR diagram for short. In a Hertzsprung-Russell diagram, the vertical axis is luminosity. This one says brightness, but ignore that. They mean luminosity here. The horizontal axis is temperature, but it's inverted so that hotter temperatures are to the left and lower temperatures are to the right. These temperatures correspond to the spectral types, and they're listed here: O, B, A, F, G, K, and M. Main sequence stars that are fusing hydrogen into helium in their cores occupy the main diagonal of a Hertzsprung-Russell diagram. When a star finishes its main sequence, it can go on to the red giant branch. Those stars then begin fusing hydrogen into helium in their shells, not in the cores, because the cores are occupied by helium and other heavier elements. If the stars are massive enough, they can then go through cycles of fusion of heavier elements. So we also have supergiants. Then when stars are done with fusion, if they're not massive enough to go supernova, they retire, so to speak, down to the realm of white dwarfs. The white dwarfs are no longer fusing any elements. Instead, they get their luminosity from emission of stored thermal energy. Our sun is not massive enough to go supernova, but we do expect it one day to become a red giant, and then, after it releases its outer envelope, to retire into the realm of white dwarfs.